Hello everybody, and welcome to our next video in Thermo, our unit 6, which is going to be about temperature versus heat, and we're going to get into a little bit of stoichiometry with thermochemical equations as well as heat of solution. Anyway, before we get into that, I want us to differentiate temperature versus heat. So we've talked about temperature quite a bit already, especially in Chem 2. And you might remember that temperature is a measure of the amount of kinetic energy that particles have. And of course, we can measure the kinetic energy by using a thermometer. So you take a thermometer, you find the temperature of something. That is a measure of how much kinetic energy those particles have. Although we're using temperature in this unit, we're more so taking a look at heat. So heat is a little bit different. We can't transfer temperature from one object to another. What we transfer, however, is heat. So heat is the form of energy that's transferred. So temperature is a measure of the kinetic energy, whereas heat is the form of energy. Let's make this red here. It's a form of energy that's transferred from a hot object to a cold object. And this continues until the two objects are the same temperature. And we're going to talk more about what that means in a little bit because we're going to actually calculate this transfer of heat. So temperature measures kinetic energy, whereas heat is more of the form of energy that's transferred. And we can measure the amount of heat that's getting transferred from one object to another. And if you remember back from Chem 2, the unit that we use as heat is the joule. So it's a capital letter Joule, and it's a capital letter J that we abbreviate it as. And the joule is defined as the heat that's required to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, so that's how much energy we need to input in order to raise 1 gram of water by 1 degree Celsius. So for example, the amount of heat that's required to raise 1 gram of water by 1 degree Celsius, you might remember this value is 4.184. And the units of this value are joules per gram degree Celsius. And this is true for liquid water, liquid H2O. So in order for us to raise 1 gram of water by 1 degree Celsius, we have to input 4.184 joules of energy. So, and we're going to talk more about what that particular value means in a little bit, but we can measure heat using the unit of the joule. So let's talk about the heat or enthalpy of reaction. So we've already mentioned endo versus exothermic reactions, and what we can do with that really is by quantitatively speaking, how much heat is coming from a particular reaction or how much heat is absorbed for a reaction. So the enthalpy or heat of reaction, and remember, we can use enthalpy and heat interchangeably thus far in your chemistry career. And this is the heat that's absorbed or released as a result of a chemical, change. So although we've said, okay, well, we can have an endothermic or an exothermic reaction, and exothermic reactions feel warm and endo feels cool, we can quantitatively determine how much heat is either absorbed or released in a chemical change. Now, because this is the heat of reaction, heat of reaction, we can in fact say that this is for a chemical change. Okay, when we have a physical process that's occurring, we don't use heat of reaction, we use something else, which we'll get into in a little bit. So for example, we're not going to use any quantitative values yet, but let's go ahead and look at some examples. So the combustion of methane. So if I take CH4, which is methane, and I react that with oxygen, I get carbon dioxide and I get water vapor, but of course I get heat from here as well. So this particular example would be an exothermic reaction, which we've talked about already, exothermic. Because this is an exothermic reaction, we know that your delta H would be negative because this is releasing heat to the environment. So if I take a look at this picture down here, exothermic means that this system is releasing heat. So the system would be the reaction that's occurring. And we'll see that the arrows are going out in this case. This means that your reaction is giving energy to the surroundings. And the surroundings could be whatever's around it. A lot of times it's air. So we can write air here. This could be water if we're doing calorimetry. This could also be your hands if you're holding the reaction. This is why something would feel warm. It's releasing heat to the surroundings, so it will feel warm. On the other hand, if I have the dissociation of ammonium nitrate, this is actually not a chemical reaction, but it's okay. We could still talk about it here. Anyway, ammonium nitrate needs to absorb heat. So notice heat is a reactant in order for this process to occur. So this is an example of an endothermic process, endothermic. And because this is endothermic, your delta H is positive. So in this example, this system, in this case, the ammonium nitrate, needs more heat in order for this process to occur. So where is it going to get that heat from? It's going to get the heat from the surroundings in this case. So this is why if you put your hand on here, your hand is going to feel cold because that system is absorbing some of your body heat in order for the reaction to occur. If your hand wasn't there, it would absorb energy from the air that's surrounding it. So we have to consider the system versus the surroundings, okay? Exothermic reaction, it's releasing energy to the surroundings, which is why the temperature for these feels pretty warm or hot. Whereas endothermic is absorbing energy from the surroundings. And this is why those will feel cold or very cool in comparison. So, and we're going to talk a lot more about this as we progress through this unit. But although these are qualitatively speaking, we haven't put numbers in here yet, we can start to put numerical values to heat. So let's take a look at the stoichiometry of thermochemical reactions. So in this first case, looks like I have hydrogen gas reacting with oxygen gas yields 2 water molecules. And in this reaction, this process is releasing 484 kilojoules of energy. So if we wanted, we could put plus 484 kilojoules. I don't have to worry about the negative sign. The negative sign just tells me whether or not this is a reactant or a product. So because I'm placing that 484 as a product, I don't have to include the negative sign. This is more for semantics to tell me where this is going, product side or reactant side. But anyway, what this is telling me is that 2 moles of hydrogen and 1 mole of oxygen yields 2 moles of water, while 484 kilojoules of heat energy is released. And we can do stoichiometry with this information, which is what we're going to do down below. I am going to try my best to get some more practice with this. If we have time, I would love to do a lab with this because I find this is super easy. But students tend to get it wrong sometimes. And I think it's just because I haven't done enough practice with it yet. So we're going to practice this quite a bit in class, and hopefully we'll get a quick lab in there. Anyway, Since the forward reaction, so in this forward reaction, when I'm going from hydrogen and oxygen and making water, this is an example of an exothermic process. However, if I consider the reverse reaction, which we can see down below, this is just the reverse reaction. The reverse reaction would be endothermic. In order for water to decompose, I would have to input energy to this. So I would have to add 484 kilojoules of energy in order for water to decompose. And in fact, this is an example of electrolysis right here. Water is not going to decompose on its own, right? We need something to help that reaction continue. And that's what the Unit 9 is all about, which we're going to do Unit 9 right after this. I think it's a great great next thing to start studying. If the reaction is a multiple of a balanced equation, so let's say I have 10 hydrogen molecules react with 5 oxygen molecules to make 10 water molecules. If this reaction is happening 5 times, so if I consider this first reaction up here and then this bottom reaction down here, notice how my delta H is 5 times that 484 kilojoules of energy. In order for this reaction to happen 5 times, I would have to input 5 times the amount of energy. And that makes sense. So just little things to keep in mind as we start going through stoichiometry with these. Let's go ahead and take a look at these 2 sample problems here. So consider the following reaction. All right, I got some production of ammonia right there. How much heat would evolve from the reaction if 7.50 moles of nitrogen reacts? Okay, so I'm going to start off with 7.50 moles of nitrogen. And of course, I'm going to have to bring moles of nitrogen down below. If I look at this balanced chemical equation, according to this, 2 moles of nitrogen requires, or will release rather, 184 kilojoules of energy. 2 moles of nitrogen, according to this balanced chemical equation, releases 184 kilojoules. So 2 moles of nitrogen releases 184 kilojoules of energy. If you want, you can keep the negative sign for this because then you would get a negative value, which makes sense. So, judging from that, that's it, right? If you have 7.5 moles and 2 moles releases 184 kilojoules, you would release negative 690 kilojoules of energy. So now I'm including not just the stoichiometry here, but I'm also including this heat of reaction in this case. So keep that in mind as we keep doing more examples with these. Let's just do one more. So it says 1 mole of propane evolves 2,043 kilojoules of heat upon combustion. So it does say it's evolving, okay? And notice there's no delta H listed here. If this is evolving, evolving means it's producing. Okay, so it's producing that much heat. So that means my delta H would be negative 2,043 kilojoules. How much heat would be evolved if a tank filled with 100 pounds of propane undergoes combustion? And it says 1 pound is equivalent to that many grams. So I do have to do a little bit more stoichiometry here, but nothing we can't do. Let's start off with 100 pounds. It's a real life problem here because think about it. A lot of people might use propane to heat their homes. We use propane in our lab, right? So we have to consider, all right, if we have propane tanks, how much heat are we going to get from those? Okay, so 100 pounds. And it looks like here, 1 pound is equivalent to 453.63 grams. So 1 pound, 453.63 grams. This is 100 pounds of propane, so C3H8. So this would be propane here as well. Molar mass of propane is 44.11 grams of propane. is equivalent to 1 mole of propane. Now we're going to use our thermochemical equation to relate moles of propane to heat. And it looks like 1 mole of propane, so 1 mole of propane, will release negative 243 kilojoules of heat. You don't have to say the negative. If you say releases 2043, you technically don't need the negative sign. You're going to kind of see how this works with semantics and wording as we progress through this, but I'm going to leave the negative sign in the equation so that way I get a negative value because technically I am releasing that much energy. And holy moly, you get a huge number here. You get negative 2.101 times 10 to the 6th kilojoules of energy. So you're releasing a ton of energy in this case, which makes sense. If you have a 100-pound tank of propane, it should release a lot of energy. We're going to do more practice with this in class. And like I said, I want to get a lab in there, hopefully, if there's enough time, where you'll actually measure the heat of reaction for something. So anyway, we'll see. But let's get on to the next section here. Let's talk about heat of solution. We might have talked about this in Chem 2, I don't remember. So reactions tend to absorb or release heat, right? So we call that heat of reaction when we're talking a chemical reaction, if I'm producing something new that wasn't there before. On the other hand, we could also have heat of solution. So your heat of solution is more for your physical process. I spelled physical wrong there, but you get it. Physical process of dissociation, right? So when we're dissociating something. A lot of times when you dissolve something in water, that particular substance might feel very warm or it might feel very cold. So for example, when I make a hydrochloric acid solution, that hydrochloric acid tends to feel very warm. However, if you dissolve calcium chloride in water, calcium chloride gets very cold in solution. So that is an endothermic process. And depending on the nature of the intermolecular forces, we can determine what's happening on a molecular level that's causing something to be exothermic or endothermic. So when we're making a solution to the average person, to the peasant of chemistry, seems very easy, right? You just put something in water and it dissolves. To the chemist on a molecular level, there's a lot of stuff that's happening, okay? The first thing that has to happen when I make a solution is that these solute particles have to separate from one another. In order for these solute particles to separate right here, that requires energy. So when I move all of these particles away from one another, that requires energy to do that. So step 1 is an example of an endothermic process, okay? We have to input energy in order to separate those solute particles from one another. On the other hand, we also have our solvent, and those solvent particles also have to separate from one another because they have to allow the solutes to get in between them. So a lot of times they have to break hydrogen bonds. If this is water, we know that we're going to have to break some hydrogen bonds because these are separating from one another again. So I'm going to draw some arrows here to show that they're separating. See, they're very close here. These are also very close, but they get farther apart. So we'll say they're very far here. This also requires energy in order to break some hydrogen bonds and in order for these particles to get farther away. This process is an endothermic process that requires energy. So the first 2 steps in making a solution, we have to separate the solute into its individual components. And a lot of times to do that, I have to break ionic bonds. If this is, for example, NaCl, there's an ionic bond that's holding sodium chloride to one another. So I have to break that ionic bond. And then I have to also break some hydrogen bonds in my solvent. Usually that's water. Both of these requires energy. we have to put energy in for this to occur. So delta H is going to be positive. This is an endothermic process. Endothermic process. On the other hand, so that's step 1 and that's step 2. These tend to happen at the same exact time. However, when these come together, when my solute particles and my solvent particles, when they form new intermolecular forces, so they might form, let's say if I have water and I have an ionic solid, these might form ion dipole bonds in between them, or intermolecular forces. When we form those ion dipole bonds, we are going to be releasing energy in that process. So allowing the solute and the solvent to interact to form the solution, when they form these new intermolecular forces or ion dipole, sometimes you could have hydrogen bonds that could form between them. Maybe you have dipole-dipole, but a lot of times if you have a salt and water, it'll be ion dipole. When I form those new intermolecular forces, this tends to release energy. It's more stable because we don't want all of this salt in one spot and all of this solvent up here. They want to interact with one another. So when they interact, that releases energy. And that's going to bring in something else that we're going to talk about in Unit 9, which is entropy. Might have talked about entropy in physics, I'm not sure. But in this case, your delta H for this third step is going to be negative. You're releasing energy during this step. So this would be an exothermic process. Exothermic process, releasing heat. Now, depending on how much energy steps 1 and 2 absorbed versus the amount of energy that step 3 released will tell us whether or not the heat of solution is positive or negative. If this particular process is releasing energy on the whole, or if it is absorbing energy on the whole. So your heat of solution for step 1 plus your heat of solution for step 2 plus your heat of solution for step 3 gives me the overall heat of solution. And this could be positive or negative depending how much energy is required for those individual processes. So let's take a look at another image here. I like both of these images for 2 different reasons. So here's a graph of enthalpy versus, I don't know, we'll say time. We'll say time is on this axis right here. So step 1. Step 1, we have to, so I have my solute and my solvent right here. Okay, they're separated at first. I put the solute into the solvent. First thing that happens, the solute particles have to separate from the solid. I have to break some ionic bonds here. This is requiring energy. So we'll notice that my enthalpy is increasing, okay? Energy, this is a positive value for enthalpy going up, step 1. Step 2 also requires energy. The solvent particles also have to move apart from one another to allow the solute particles to enter the liquid. Now, here's when we can tell whether or not this reaction is endo, or whether this process is endo or exothermic. So step 3 is when the solute particles are attracted to the solute particles. This releases energy, this step right here. Notice how this process releases more energy than the first 2 steps total absorbed. So right here, I have a difference between the energy that's absorbed versus the energy that released. Because this particular dissociation released more energy than it absorbed, this particular dissociation, this heat of solution will be negative. This is an exothermic process. Let's say that maybe I had this, but what would it look like for an endothermic process? An endothermic might look something like this. Maybe this is where your heat of solution ends up, okay, notice how the amount of energy that's absorbed is greater than the energy that it released. So here's my difference. But my products are higher than my reactants. Here, my products are lower than my reactants. This would be an example of an endothermic. So we're starting to bring in those reaction profiles with these as well. And the more we look at them, I think the more comfortable you'll get with them. But that's how we can tell whether or not a solution will be, or a heat of solution will be positive or negative. So let's define the heat or enthalpy of solution. And just to reiterate again, enthalpy and heat mean the same exact thing for us at this point in our chemistry careers. So the enthalpy of solution is the amount of heat energy that is absorbed or released in a specific amount of a solvent, of a solute, dissolves in a solvent. But you probably got the idea of that already as we were progressing through this, okay? Oh, not what I wanted to do. And here are some values of heats of solution, okay, for a whole bunch of different types of solutes. So I have silver nitrate right here. I have, I don't know what that is, ethanoic acid. I don't remember. Potassium chloride, potassium chlorate. I have sodium hydroxide, and we'll see these values that are here. Whenever I see a negative value, so for example, potassium hydroxide has a negative enthalpy of solution, this means that this is an exothermic process. This is releasing heat in the process. If I take a look at ammonium nitrate, on the other hand, this is a positive value for enthalpy. This would be an endothermic process. So the amount of energy that's required to separate water and ammonium ions and nitrate ions is greater than the ion dipole bonds that are formed when we make the actual solution, okay? And there's quantitative values there that we can look at. We might do a lab with this as well. Again, it all depends on time. But if I take a look at this right here, these are the enthalpies of solution per 1 mole of solute right here. So this is per 1 mole. So if I consider this ammonium nitrate, 1 mole of ammonium nitrate has to absorb 25.69 kilojoules of energy in order to dissociate into its ions, like this. So I would include 25.69 as a reactant. Here, if I take a look at, let's see, oh wow, hydrochloric, look how much energy is released there. Hydrochloric, again, 1 mole of hydrochloric, so 1 HCl molecule, will dissociate into its ions, but I also have 74.84 kilojoules of energy that's released in that process as well. So we'll look at some examples with this in class, but otherwise, I think College Board really wants you to understand these charts more than anything with heats of solution. I always see a ton of charts pop up on the multiple choice questions. So we'll do as many of those as we can. We'll take a look at as many of those as we can. So just to reiterate, the heat of solution will be negative when heat is released, and it will be positive when heat is absorbed. And that's when it feels cool. Like I said, I think those diagrams are the most important in this case, but also the stoichiometry with thermochemical equations is also pretty darn important. I actually did your progress check last night just to kind of see what it was about, and there were a lot of multiple choice questions dealing with stoichiometry with thermochemical equations. So we're going to focus on that pretty heavily in class. As always, if you have any questions, make some notes and let me know. Otherwise, I will see you in the next video all about calorimetry and thermal equilibrium. I will see you then. Bye.